Getting good at this. Okay, now this was a very unsuccessful question for you guys. Partly because this table I think confused you. I hadn't really done one of these with you. Guys, if you didn't listen to anything, this is the time to listen, because it's one we didn't do very well on. This is called a probability table. It's saying along the top of a probability list the possible outcomes that could happen, and below it you should be writing the probabilities of those things. So somehow we need to read this situation and realize what the chance of 0, what the chance of 1, and what the chance of 2 are. There's a bit of a hint here. There's some space, so they're probably expecting a diagram of some sort, or at least some calculations. Alright, so reading the question. Previous studies have shown that 1 in 10 people suffer from a disease. The disease can be picked up with 100% accuracy from a blood test, so it's a perfect test. In the following cases, the test was conducted on blood samples that had been submitted to labs to arrange. So there's two sets of questions around this. Alright, this is trying to explain what the table means. Let X represent the amount of positive tests, people having the disease, from 2 random tests. So there are 2 tests coming through. You could get none of them are positive, you could get one of them as positive, or you could get both of them as positive. That's the connection between the table and X in the situation. So it's a tree diagram as your method here. The first test could either be positive or negative. The second test could be positive or negative. If it was negative the first time, same results. Okay? So where do I go on this tree to get no positive results? I'd need to go negative, negative. What are the chances of getting negative, negative? Well, if I use numbers, there's a 0.1 chance of being positive and a 0.9 chance of being negative. Alright, 1 out of 10 is what? 0.1. 9 out of 10 is 9 over 10. So 0.9 times 0.9. Or 9 over 10 times 9 over 10. You do that calculation, you get 0.81, I think. Yeah, 0.81. Okay, now I'm going to take the shortcut here. I'm going to go to the other easier one to do, the chance of getting 2 positive tests, which is to go positive, positive. Positive, positive is a 0.1 times 0.1, which is quite a small number, 0.01. Alright, 1 over 10 times 1 over 10. Now, I could go through and calculate the chance of getting 1 positive by going negative, positive, positive, negative, add those probabilities together. But these probability tables always add up to 1. If these are the only outcomes, then all 3 of these numbers add up to 1. So far I've got 0.82. That must mean I've got about 0.18 left over. Alright, taken away from 1. Okay? So, you got a mark for getting the numbers in the table correctly, an achieve mark. You got a mark for doing some calculations to get there. Alright, so 2 achieve marks there possibly. Okay, question B. Another random sample of 4 blood tests found, so 4 blood tests, not 2 this time, found that 3 of them had the disease. We're not saying that the odds of 1 in 10 have changed, we're just saying that someone observed, 4 tests came in, and 3 of them turned out to be positive. So that seems pretty unlikely. We're going to figure out how unlikely that is. One option is to draw a really massive tree diagram that's got positive, negative, positive, negative, until I've got 4 sets of branches all the way through it. Alright? Then what I'd have to do is I'd have to figure out how many of these pathways through the tree give me 3 people positive. So positive, positive, negative, positive, negative, positive, all the different combinations that would do that. Alright? If I started doing that, and I did it this way for instance, positive, 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 negative, I'd end up with 0.1 times 0.1 times 0.1 times 0.9. Alright? Positive, 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 negative, multiplied. Alright? If I did it in a different way, I'd end up with the same calculation. 0.1 times 0.9, so positive, then negative, then positive, then positive. You see that I'm actually doing the same calculation each time, just the order of multiplications change. So I always get the same answer. So what I realize that I can just find out how many different ways I could get 3 positive results and then multiply that by this. So that's my question. How many ways could I get 3 positives out of 4? Your options are list them all or use combination theory. Okay? So if you want to use combination theory, what you're saying is that there are four things you're going to choose, 4 tests to choose, and you want 3 of them to be positive. How many different ways can you order 3 things from 4 things? Okay? And that turns out to be 4, only 4 ways. Alright, if you listed them all, you've got the same answer. There are 4 ways to do that. So you're going to go 4 times 0.1 times 0.1 times 0.1 times 0.9. The 4 different options there. Okay, and the answer comes out as 0.0036. So if the disease is actually this prominent, 1 in 10 people have it, this is the chance of you getting 4 tests that come through with 3 positives. Less than 1%. So that seems pretty rare. Seems like something like that is either a really bad coincidence or something's gone on. To get the 1 out of 10, you mean? The original results? Yeah, I mean, you can get only 4 things happening. Yep, I can accept that a little bit. What else could be happening? Why could we have got much? Could we have got this result when the odds of it happening are so low? Yep, so if the odds of the people we were testing weren't 1 in 10, they were higher for some reason, okay, because they were, for instance, people who had visited doctors lately. So if your health has gone not that well, then there's a greater chance of you having this disease because that disease could have been the reason that you got unwell. All right, so that's a very good explanation, I think, if you can talk about that properly. So let me write this somewhere. So that's our odds. Always a good one to talk about is independence. But just saying independence won't get you your excellence mark. You've got to apply the idea of independence to this, and the question said, and comment on its validity, I think, and justify their validity. So, is independence valid here? Is there any connection between these people, perhaps? And the answer would be independence is assumed, but may be invalid. Because. Justifying often has the word because in it. So what reasons will we have to believe that these people might be more likely to have the disease? So if the first person in a group of 4 people walking into a hospital has the disease, is there any reason the person behind them might also have it? Yeah, it could be contagious, or they could be related. Often people visit hospitals together, and so if they're just going along for a random test, they might be related to each other. So one person having it might make it more likely that the person they're related to has it. Okay, so it might be invalid because these people may be related, and therefore have the same genetics or environments. I don't know if you guys ever watched that House program, but normally when something weird happens, they would either go investigate the person's house to see what environment might have affected them, or they would ask about their sort of history, what diseases they had in their family and things like that. So that's the kind of idea we're talking about here a little bit. The other one is what Healy was talking about a little bit more. These people may not be a group who has a 1 in 10 chance of the disease. Okay, Now, that's not good enough, I don't think. I need to think about what reasons they might have to be higher risk than what we're saying. Okay, so here's an example. Because they could be submitting blood because they're already sick. Or have some symptoms. Okay, so in summary, what we're getting at is that there was a very low chance of getting 4 blood tests and having 3 of them as positive. So we're trying to explain what reasons there might be for that, because this is the idea of true probability and model probability. Okay, true probability is the actual chance of something happening. Model probability is normally based on some calculation which involves a whole bunch of assumptions. So you're trying to find the differences between what's really happened and what the model's trying to tell you has happened. Okay? Alright, so just